Yes, class. So today we have to start with second lesson, that is electric potential and capacitance. So first we'll complete electric potential, then we'll move on to capacitance. Now see, from this part, electric potential and capacitance, lots of integration and differentiation are used, as I have discussed with you. So since many of you were not with me in class 11, so let us just quickly discuss this differentiation and basics of differentiation and integration. See, when you have, though we have discussed some of the portions in dimension analysis also wherever, but now wherever this is required, we'll use. So before starting with the lesson, quickly just revise differentiation and integration. The very basics of it we are going to discuss, because in potential you have lots of concepts of differentiation and especially integration. Integration is used often. So that's why. So suppose we say we have, let's say, y is equal to x to the power n. So power gets subtracted from 1 minus 1 and the constant term comes out. For example, you have x square. So 2 minus 1 will be there in the power and this 2 comes out, which is the constant. So similarly, let's say dx, x to the power 5 by 2, I have to differentiate. So this becomes 5 by 2 is the constant. So I'll bring it out. X to the power 5 by 2 is left now. Subtract 1 from. That becomes 5 by 2, x to the power 3 by 2. Similarly, x to the power half if I have to differentiate. So this becomes half comes out, x to the power half is left now, subtract 1. So that becomes half, x to the power minus half. This is how we perform the basics of differentiation. Now, just remember the properties of differentiation before moving on to integration. Yes, coming to the properties of differentiation, just remember, if you have a constant term and you are differentiating only the constant term that is present, just the constant term, if you're differentiating, it would be 0. Like, for example, if I give you 3, if I give you this number 3 and I ask you to differentiate 3, 3 is a constant number, differentiation of 3 will be 0. If I give you a constant number like pi is a constant, 3.14 is its fixed value. So when you differentiate pi, that also becomes 0. Suppose you have a constant and a variable together. If constant and variables are together, like 2x square, 2 is a constant, x square is a variable. So what we'll do, just bring the constant term out and differentiate the variable the way you have been differentiating. How will we differentiate x square? This is just dx over dy. This we have to do. So see, if when we are differentiating this, y will be equal to 2. Now x to the power 2, the constant comes out. What is left? X to the power 2. Subtract 1 from it. That makes it 2 into 2x, which is equal to 4x. So all of you must be knowing all these properties already. It's just that for a quick revision. If a constant term is there and only the constant term is there, no other term is available, directly you will put it as 0. But if you have a constant term getting multiplied to a function, that is function of x, function of t, time, function of s, any variable, bring the constant term separately and multiply it with whatever is the actual answer of the differentiation. Fine. So quickly just write down revision of calculus, write differentiation part first, then we'll discuss integration. And then we'll start with potential. So as I'm seeing, first we'll complete, this chapter is divided into 2 parts, electric potential and capacitance. First part is electric potential, that involves your potential and potential energy, potential due to point charge, the way we have been studying whatever topics for subtopics for electric field. And then separately you have capacitance. So capacitance is a different topic that we'll see later on. We'll first focus on electric potential. Yes, Madiha. Madiha, this is your first class, no? Madiha Irfan.
Ma'am, this is my second class. I was not attending classes because I had my test going on.
All right, all right. You have attended class. So, which topic was it when you left it?
Ma'am, it was the first chapter, and we were doing like from Torque. From Torque, I left.
Okay, okay. So, see, Maria, that chapter is over. This is the first class for chapter 2. So, I think the right time you have joined it because today is the first class. And before starting with the next lesson, no, it's just that some revision of calculus is required. That is what I'm doing, differentiation and integration. After this, we'll start with potential. Fine.
Oh, okay, ma'am. Yes, ma'am.
And
Okay.
please take just have a look from the video lectures because lots of portion is included over there.
All right, ma'am.
That is with respect to this you're asking. This is with respect to differentiating something with respect. Done till here?
Ma'am, I'm doing 1 second. Done, ma'am.
Others also have completed. If anyone is writing, just stop me. Now, one last property that is left is addition and subtraction. See class, wherever addition and subtraction is given to you, I'm not discussing this in detail because wherever in the numerical or in the derivation portion this will be asked, I'll discuss it at that point only. See here, when addition and subtraction is asked, no, then what you do, the way you individually differentiate it, the way you individually perform differentiation, x cube, x square, x, perform differentiation, and whatever is the operation, put it in. For example, first one I'll practice, rest of it no need to write. X cube. So that becomes 3x to the power 3 minus 1, that is 2. So plus x square. X square becomes 2x to the power 2 minus 1. That becomes 1 plus x to the power 1 is already there. So 1 minus 1 becomes 0. So x to the power 0. And see x to the power 0, this is 1. So you can write this equation as 3x square plus 2x plus 1. Or you can even see it in this manner, dx over dx you are writing. So that will cancel and become 1. This way we perform differentiation whenever mathematical operations are. Whatever is given, whatever operation is provided to you, if it is instruction for addition, if it is instruction for subtraction, added and subtracted respectively. Fine. This is just note this line till here. Just note this example. One example at least. Make heading addition and subtraction and write just this example. Then I'll start with integration. See, for integration, Just remember the steps for integration. See, if you are given, we'll practice examples. If you are given, let's say x to the power n, you have to differentiate and limits are provided to you from x1 to x2. So what we do, add 1 to the power, x was there, x to the power n, add 1 to it. Now whatever is the power that is obtained, divide it, n plus 1, and put in the limits. Once this is obtained, then this is a constant term separated. Whatever power you have obtained, no, put in the limits. First the upper limit, x2 minus the lower limit to the same power. For example, if we have this differentiation 4x cube, 4 is a constant, whether it's integration, differentiation, 4 we separated. X to the power q, right? What did we learn? Add 1 to the power. So plus 1 to the power divided by whatever power is obtained now, what power you have obtained right now, that is 3 plus 1. This comes in the denominator. Limits 1 to 2. So this becomes 4 x to the power 4 divided by 4 limits from 1 to 2. So 4 gets cancelled. Now, next step is putting the limits in place of powers. So first we put 2 in x and then we'll put 1. So 2 to the power 4, then operation is minus, negative, subtraction, minus 1 to the power 4. So this is your complete answer, 2 to the power 4 minus 1 to the power 4. Now no variable is left. This is your answer. If you have 4x to the power minus, right? If you have x1 to 4 divided by x to the power minus 2. So no change will come here. It becomes x to the power minus 2. Rest of the steps remain same. Plus 1 here, minus 2 plus 1 in the denominator, then putting the limits minus 1 to plus 1. First this limit will come, then that limit. This is how we solve it. That's it. Fine. So if you are asked to perform integration, and in integration, because when we'll do potential, so in potential, it will be used a lot, especially integration, more than differentiation. More differentiation you also have when you have relationship with electric field. So this complete this. This is 2 to the power 4. So that becomes 16. 16 minus 1, this is 15. So you get a one complete answer for this. This also you can solve further. This I'm leaving up to you. This is just an example, but note down at least this example and the steps for integration. Then we'll start with what is electric potential. Just text done once you have written till here. Which one? The differentiation part you're asking? This one, properties. Okay, noted. You're getting this as 0. No, I don't think so. It would be 0. See, this is 4. Let me write it. 4x to the power minus 2 plus 1. Minus 2 plus 1 will be here. From minus 1 to plus 1. So this 4 becomes common. X to the power 1 minus 2. Minus 1 divided by 1 minus 2. That is minus 1. So directly the power is minus 1 to plus 1. So this becomes minus 4. This power gets multiplied. Firstly, okay, let's substitute the values of x. So positive 1 to the power minus 1 minus negative 1 to the power minus 1, right? This is how we substitute in the formulas. Now see what we can do, because this is negative, minus 4, this is 1 by 1 we can write, so that this becomes positive, minus, this minus minus becomes plus, and this also if we shift it in the denominator, this becomes 1 by 1. So see, minus 4, 1 plus 1 is 2, that is minus 8. I think, Madiha, you must have committed error here. You must have taken this as negative. See, this is minus minus will become plus, right?
Ah, yes, ma'am, that's what I made mistake. Yeah,
So,
yeah, yeah.
this should be the answer. If anyone wants to note it down, you can. Otherwise, I think we can start with the next lesson. Somebody wants to note it down?
Ma'am, just a second, just a second. Ma'am, can you please scroll down? Yes, ma'am, done.
Now class, coming to your chapter 2, that is electric potential and capacitance. Now see, this is also part of electrostatics only. Here also I'll not be using the terms acceleration, velocity for charges. Your charges are at rest. The way in electrostatics first lesson, electric charges and field, we had seen no charges were at rest. We were talking about forces but not acceleration. So same thing here also. This is also second lesson from the first unit only, that is electrostatics. So capacitance is slightly different, but electric potential is very much similar to whatever you have studied till now. Just a quick revision of work done. Work done, I hope all of you must be remembering, because work done will be used here a lot. If your force is constant, we use no dot product of force and displacement, F dot S, Fs cos theta, when your force is constant. If your force is variable, so we perform integration F dot dx, integrating it from the whatever displacements are provided from x1 to x2. This is for variable force. This is the revision from your class 11th. In class 11th in work, energy and power, you must have done work done. Formula of work done, Fs, F dot S, Fs cos theta. F and S are the magnitudes of force and displacements respectively. And F dot dx is for a variable force. Now, this was just a revision. You will be needing it later. But right now, what is electric potential? See, electric potential and electric field, these are actually the exact things. These are very much same things. But difference lies in the fact that this is just the scalar form of whatever you have studied. Electric field was a vector quantity. Remember, for even solving just two quantities, we had to apply and keep in mind all the laws and directions of it. That is not valid in potential. Potential is a scalar quantity. You can directly algebraically add all the quantities. You can algebraically subtract all the quantities. There isn't any issue over there. If a potential is coming negative, you will consider its side and you will subtract it directly without considering the angle. So electric potential, if I give you a source charge, for example, if I give you a source charge, let's say plus Q. So this charge will be having a field around itself also. And if I take, let's say this is the source charge. This is the source charge. If I take just the difference that lies in electric potential and electric field is that I have taken this charge, this particular test charge, from infinity to this particular point. This charge is kept in infinity. So from infinity, this is what? This is the test charge. So from infinity, I'm bringing one charge, and let's say here I have kept my capital Q. Fine, here I have kept my capital Q, that is source charge. Source charge is stationary. It is producing some electric field around itself, some potential around itself, some sort of properties around itself, forces around itself. Now I am bringing this small q. As soon as I am entering, suppose this point, let's say this point is A point. As soon as I'm entering this point, some forces are felt. It means some field is existed, and that we had discussed. This is electric field. So just the scalar form of it, or whatever is the work done that was required, whatever work done was required by us to carry that charge from infinity to the particular point A. That is what is meant by potential. Here you have the involvement of work done. Here your charge comes from infinity and all of the quantities are scalar. That is just the difference which you have to remember for electric potential. All right. So do not worry about your all the concepts for the angles that are given, whether parallelogram law should be used, putting all the Cartesian unit vectors, I cap, j cap, no need. Electric potentials calculations are very much easier. It's just that wherever work done is required, you have to perform integration. Otherwise, this is a simple lesson. So coming to the definitions, yes, it defines the electrical properties around the charge in scalar form, and only electric only force that we have studied through Coulomb's law, they require two charges minimum for each other to exert force. Yes.
This is electric potential.
Repeat. Should I repeat it?
No, I'm like, I thought this was potential energy.
No. This isn't potential energy. See. Potential energy is different. We'll come to potential energy. Potential energy, when we talk about potential energy, in that case, two charges have to be there. And whenever we are talking about potential energies in any form, not only this just particular electrical potential energy, in your 11th also you must have studied gravitational potential energy. So whenever potential energies are there, the force has to be exerted. Two particles, two charges will exert force on each other, and that's what I was saying, that for force you need minimum two charges. Electric field is a property of a single charge. Electric potential, this is a property of a single charge. So it defines electrical properties around charge. But the difference is that potential is actually the work done. This is not energy, it is the work done. But by what? When it is a potential will only be equal to work done when your charge is a unit positive charge. How this is possible, I'll tell you. See, let's say this is my final point, some potential is here, and this is point at infinity. So what will be the potential difference? How to take the potential difference? Final potential minus initial potential means potential at a point minus potential at infinity, right? This is actually equal to work done from infinity to a to carry this charge q. This is the formula that you have to use, you will be using. So we take the potential as work done divided by charge. Had it been potential energy, there wouldn't have been anything in the denominator. It would have been directly equal to work done. So potential, this is the formula that we use. So if I say somehow, if I make this q as +1 coulomb, can anyone tell me what will be left in this formula if q is +1?
Then electric potential will be equal to work done.
Exactly, electric potential will be equal to work done. So if this is the condition, then only we can say potential is equal to work done. So we have got one more definition to define, right? And that you can put in your answers also in your exam. So what is potential? Potential is the work done, but this is incomplete because otherwise that will become potential energy. So how to differentiate it from potential energy? It is work done in carrying unit positive test charge, a single unit positive test charge. In energies you have more than single charge, that we'll see when we'll come to energy. So it is work done in carrying a unit positive test charge, means +1 coulomb from infinity to a particular point against electric field and also without acceleration. Why against electric field? Why without acceleration? Because see, without acceleration, so obviously because we are considering electrostatics and our charge is at rest. So no need to define and bring out all these terms like acceleration, velocity. And why against electric field? This actually has a lot of detail. Why against electric field? You have a proper section for it. So I think that time we will discuss it. That would be better because right now, otherwise things will get mixed up. All right. So this is how you define electric potential. Work done in carrying unit positive test charge from infinity to a particular point. This way you will remember the definition also, and this way you will remember this formula also. V is equal to work done by Q. Just remember this is a scalar quantity, no need of the headache for all the, this is a scalar quantity, and SI unit is, see, for work done is a form of energy. So, and the SI unit, standard SI unit of work done is joules, and divided by charge, right? Work done per unit charge is coulomb. We use the unit joules per coulomb, but we have a specified unit for joules per coulomb also, which we write it as volt. You will see 3V, 2V written as. So that is SI unit, and it's a scalar point. Before going on to this topic, electric potential for a point charge, you should write down all these points. Wherever doubts you are having, let me know. This is the starting of the lesson, so you can get your concepts basics clarified. Written, all of you, till here. Done? All right. Now see, electric potential for a point charge. So see, we can calculate this for a point charge. Why? Because it's a property of a single charge. It is independent of other charge. Even if a single charge is present, it will exert its own electric field. It will exert its own electric potential, but it won't exert its own force, right? If I have two charges, they'll be exerting force on each other. That's why we have Coulomb's law, where two charges are involved. Remember, F is equal to K Q1 Q2 by R square. Electric field, we had only single charge. E is equal to KQ by R square. One single charge. Here also we'll find out. See, for example, this is point A. Let's take this is some point. The entire separation from this point, this is, let's say, dx. Fine. At this particular point, I want to carry this charge. This is, let's say, small q. I'm carrying this from small q to infinity. This is, I'm carrying from small q to infinity. Now, see, there will be exertion of two. One will be force that will be, two charges are present in the system. One capital Q, the stationary source charge. Other one is the movable, your test charge. So two charges are there. One force will be there. And one external force will be there, which we are applying to make this charge Q move from its infinity to come to a point. Yes, Chavez?
Can you repeat again? My Wi-Fi is little slow.
Okay, see. This is just a case that I have taken. Charge Q is present, point A is kept, where the separation of charge Q and A point is smaller. Now, I have taken a point that is small q. This is the test charge that I have taken. Now, see, at this particular point, no, from the entire separation from this charge capital Q, I have taken this as dx. The separation from this capital Q, this I have taken as dx. Now, two forces will act in your system. One force is the external force that you are putting to shift the charge. No, the definition of electric potential, this is what we had studied, that we bring the charge from infinity to a particular point. So one force will be this, the external force which we are putting. One more force will be there, which is the internal force within the system, because two charges are present, so they'll be having electrostatic forces also, right? So what will be the force? Magnitude of F, this force will be K capital Q small q divided by dx, right? Or let me take it as x. Let me take this as x, because separation is not so small, no? So why to take x dx? So this is x, so their formula will become this first element. According to Coulomb's law, if I substitute Coulomb's law in here, two charges are there, capital Q, small q, their separation is x. So according to Coulomb's law, their force will be K capital Q, small q by x square. And one force is this external force, which we are doing, the work done that is generated. What will that force be equal to? I hope you're understanding there are two forces. That is F dot dx. This is the force in the work done formula, where we put the force which we are intentionally bringing to bring the charge small q to its position A at A point or near capital Q. So this is going to be F external dx, right? But see, this we are bringing it, this displacement is occurring in one direction towards the right side. Force is occurring in the left hand side. So it means their angle is 180 and cos 180 will become -1. So this is till now the scenario. F external. Why? Because cos 180 degree will become -1. That's why this is minus. Now see, dw, work done. So again, I have to integrate it. Now see, until and unless both the force. Yes, Shaved?
Here how angle is 180 degree.
180 degree, the angle is, see, displacement that has occurred, initial displacement, is towards the right hand side, right? Up till now. And F external is acting towards the left hand side. So we chose this, the angle becomes 180 degree, one here displacement, force is acting here. Now see what is happening. When will we able to move the charge? Until and unless F external is balancing F, then only no we'll be able to move the charge. If capital F, this force, this electrostatic force is greater, so this will push the charge away. We won't be able to bring it to its destination. So when it will be equal, if one at a particular point they are equal, and also F external and the force, they are always negative of each other. This remember, F external and the force they are occurring, they are also negative of each other. So now if you substitute in the value, that also if you see, from that also if you see, even if you do not put cos 180 degree, let's say we are considering the charge, let's say we are considering this force, F. So for force, we are bringing the charge towards Q. So let's say this displacement is also occurring towards the left hand side. Force is also occurring towards the left hand side. But why did I take negative then again? Because this is also one more relation, that F external is negative of X. So in the formula, what can I do? I can substitute F external. Let me write it positive here. So I can put F external as minus F dx, integrating it from whatever value is given, point R to X, right? Now see, just we'll focus on this. A limit. Limits will be what? From infinity, we are bringing it, we are carrying this to R point. So limits are from infinity to R. F external is equal to minus F. That's why I have kept minus F. Now it will become easy. Forget that angle concept. Now it will become easier than before. And what is the magnitude of force? We have calculated from Coulomb's law. K capital Q small q by x square dx minus integrating it from infinity to R. This is, I've just kept the value of force as K capital Q small q by x squared. This is what we had seen. Now see, we just have to substitute it. That's why we had just revised integration also. Now you will be able to solve it. See, all the terms are constant. Minus K capital Q small q, these are constant. What is left? Dx over x square, we have to integrate it from infinity to R. How will we integrate it? So we have discussed left, no, whenever this question we have seen today also. Write it as x to the power minus 2. Fine. If you write it x to the power minus 2, that becomes easier. Now see, add 1 to it. Now whatever is the power, minus 1 plus 2, minus 2 plus 1, we put it in the denominator, and the power we leave it as infinity to R. What is left? X to the power minus 1 by minus 1. This is from infinity to R. This is what this was the step that we had seen, right? So one thing that you can do in order to just make this as positive, we can write this minus 1 separately. Just put the minus 1 separately. 1 x to the power minus 1 can be written as 1 by x from infinity to R. This becomes now here your integration becomes easier. See, it means you can say for this particular point, you can say that minus K capital Q by small q, and this term, we have solved this aside, that becomes minus 1 by x integrated from 0 to infinity to R. This minus into minus, this becomes positive, K Q Q, and what is left over here for this? This is, we are calculating the work done. And what is left from here? We have 1 by R minus 1 by infinity. See class, 1 by infinity is always 0. So you are left with K capital Q small q by R. This is the work done. So is it sufficient? See, this is the work done that we have obtained. And what was the formula for potential? Potential is work done divided by charge. So work done is K capital Q small q by R. divided by this charge. Charge gets cancelled. You get the value of potential as kq divided by small r. See, I'm repeating. Force was k q1 q2 q square by r square. Electric field was k q by r square, and potential is k q by r. You can put in the value of k as 1 by 4 pi epsilon naught also. You can, wherever needed, this is the same k, 9 into 10 to the power 9. All right, this is the same thing. So what did we do? I'm again repeating the steps. Work done, we have calculated the Coulomb's law of force through Coulomb's law. Now work done is what? Work done is F dot ds. So force's value we have put kqq by x square. Now 1 by x square we have integrated it, and 1 by x square becomes 1 by x, right? This becomes minus 1 by x. Actually, this becomes minus 1 by x. So this minus and this minus made the quantity positive, plus, as well as it got multiplied kq by q, kq into q divided by r, because this entire term is 0 in 1 by infinity is 0. So work done was obtained as kqq by r. 1 qq gets cancelled, so potential becomes kqq by r, kq by r, where q is the charge, k is the dielectric constant, 9 into 10 to the power 9, and r is the separation. Now see, if you're getting this as a positive charge, since it's a scalar quantity, your potential will become q by 4 pi epsilon naught r. And if it's a negative quantity, it will directly become minus q by 4 pi epsilon naught r. First, tell me, any doubt still here? Is it clear to all of you? Austin, Faiza, Madiha, Tarif, Chavez.
Yes, ma'am.
Yes, sir.
All right then. Note down, this derivation is asked in your exams.
Potential will be negative.
Yes, potential can be negative. Here potential will be negative. Where we are having negative charge, so it will be negative. Otherwise, we used to write, no, for electric field, we always used to write the magnitude, because at the end we have to substitute it. But right now, potential can be negative. It's a scalar quantity, so it can be negative. It's a scalar quantity, so you can subtract it. Negative means you are subtracting. If it's a negative charge, you are subtracting. If it's a positive charge, you are adding it. All right, so this derivation is asked in your exam. Derive the expression for electric potential for a point charge. So you have to use these steps. Otherwise, for calculation part, just this is enough. This part is enough. KQ by R. Use this. This will give you most of the answers. We'll see some questions also. First note it. This is Austin. See, F external is minus F. This is according to Newton's law, right? Third's law is what? Action reaction. So F external is the force that is counterbalancing. It is in response to the force that is occurring in because of electrostatic force. That's why this is just by default the Newton's law which we use. This is the same thing. No other concept of electrostatic is applied over here. Done?
Yes, ma'am.
This part also, all of you? Okay, one numerical, let us see. Then from this topic only, based on this. So a very easy question this is. This says that a charge is given -3 millicoulombs. It is separated from a point A, that is the separation is given as 9 millimeters. You have to calculate the potential. So potential, the formula is K Q by R. What is K? K is the constant, 9 into 10 to the power 9. Charge is given as -3 millicoulombs. So we'll convert milli. That is -3 into 10 to the power -3 coulombs. And R is 9 millimeters. That is 9 into 10 to the power -3 meters. Right, I've just made everything into its SI unit. Now put in the formula. K is 9 into 10 to the power 9. Q is -3 into 10 to the power -3. Separation is 9 into 10 to the power -3. 9 gets cancelled. 10 to the power -3. 10 to the power -3 gets cancelled. This becomes -3 into 10 to the power 9 volt. This is the answer. Note it down.
Ma'am.
Yes, say Madhiha.
Ma'am, 1 microcoulomb is equal to 10 to the power -6 coulombs, right?
Yes, 1 microcoulomb. Here we have 1 millicoulombs.
Oh, okay.
Test for first chapter Friday. Test is on Friday.
First chapter.
Yes, first chapter will come. This won't come, what we are studying today. Electric charges and field will come. Topics, Harif, see, one test you have already given, and the rest of the topics that came, dipole, we have done the lesson, no, electric charges, field and charges. So till here, I think you had, so dipole moment, torque, electric field lines, and the Gauss theorem part. This will be included. Yes, I'll share the link, Faiza. I'll share the link of this. So on Friday, you'll be having the test. Done. Just text me done in the chat column once you have written till here. This n charges I'll do in the next class.